Alright, so we're going to be doing day 18 right now, talking about measures of location using the standard deviation as a ruler. And a little information here. Suppose that a professional soccer team has the money to sign one additional player, and they are considering adding either one goalie or one forward. The goalie has a 90% save percentage, and the forward averages 1.2 goals per game. In this league, the typical goalie saves 86% of shots, so this would be the league average for the goalies, with a standard deviation of 5%. While the typical forward scores 0.9 goals per game, that would be the mean of the forward scoring average, and a standard deviation of 0.2. Who is the better player at his position? The goalie is 4% higher than average, and the forward is just 3.3 goals higher than average. But since we're comparing different units, we can't just say the goalie is better, since 4 is greater than 0.3. To make a comparison possible, we have to consider where each player falls in their respective distributions. So basically, we're trying to decide who to hire. And we have we're comparing apples to oranges, two totally different things. So what we're going to do is we're going to standardize their score. And we're going to be calculating something called a z-score. Okay, which the blank is actually standardized score. So we're computing their standardized score. We're making it so that it basically has no units, because the goalies is percent of shots saved and forward is goals per game. They're two completely different measures. So what we do is we take that observation, we take the goalie's average saves. Our goalie saves 90% per game. So this is our observation value, observed value, minus the mean, and then we divide it by the standard deviation of all the goalies, and we get 0.8. Now this z-score measures the number of standard deviations above the goalie's mean. So this goalie is not quite one full standard deviation above the mean for goalies' average shot saved. The forward averages 1.2 points per game minus the average of 0.9, dividing by the standard deviation, gives us the forward averages is 1.5 standard deviations above the forward mean. Who is the better player? The forward is the better player because they are farther above average than the goalie is. The forward is 1.5 standard deviations above the average. It means they're higher above, they're better. So the forward is the better choice of someone to hire. So when we're using standard deviation as a ruler, okay, the standard deviation is from the last example that we had in our previous day 17 notes, most of the observations should fall within one standard deviation. That means your average person will score within one standard deviation of the mean. Outliers above the mean, farther above the mean by 1 or 2 standard deviations, they tend to start becoming outliers. Okay? So we're using the standard deviation to guide where our outliers fall. Okay? The standard deviation is a ruler to measure how far an observation is above or below the mean. We're using a standardized score or a z-score. And this is the formula for a z-score. You need to know how to find a z-score all year long. It's not going to be, I learn it for this test and I don't need to remember it. It's all year long. So it is the mean, it is the observed value, your observed value, minus the sample mean, divided by the standard deviation. And that is a z-score. And a z-score measures how far you are above and below the mean. How many standard deviations. This is key phrasing right here for when you name a z-score. Using standardized scores has a lot of advantages. Since these scores have no units, you can compare values that are measured on different scales with different units and from different populations. Suppose that a distribution of male heights has a mean of 69 inches, so the male mean, male. The X bar of the males, you can use little letters to help you distinguish. So the X bar of the males is 69 inches, and the standard deviation of the, you could say, of the males is equal to 3 inches. So that means that many males are 69. Most of them will be within 3 inches above and below. A few will be within 6 inches above and below, and even fewer will be within 9 inches above and below. All right, and for a female, the X bar of the females is 64 inches, and the standard deviation of the females is 2.5 inches. So who is taller, relatively speaking, a 65-inch tall male or a 60-inch female? All right, well, we typically know that males are taller, but who's actually taller in relation to the rest of the males or females? All right, so let's see. Let's use our z-score formula. We take our observed value, this is our x, this is our x bar, and we subtract from it the mean, and we divide it by 3. So that would be -4 divided by 3, which is the z-score for this male, who's 65 inches tall, is -1.3, repeating, standard deviations below the mean. So 65 minus 69 divided by 3 is -4/3. Divide that, -1.3, repeating, standard deviations below the mean. I want you to write that every time you find a z-score, that it's standard deviations above the mean, standard deviations below the mean, just to get you used to what the z-score is telling you. So for the female, we're going to have 60 as our observed minus the mean of 64 and divide it by 2.5. So 60 minus 64 divided by 2.5 is -1.6. So this female's z-score is -1.6 standard deviations below the mean for women. All right, so who is taller, relatively speaking? Well, they're both not even as tall as average. So who is actually taller, the 65-inch male or the 60-inch female? Who's less far below the mean? Well, that would be the male. So the male is actually taller, relatively speaking, compared to other males. All right, so now we have an exclusive club. So you'll have problems where you have to do comparisons like this in your homework. You'll also have problems like this. An exclusive club allows only members who are especially tall. The height requirement for women is 72 inches. What is the equivalent height requirement for men? So in order to fit into this exclusive club, it only allows members who are especially tall. The height requirement for women is 72 inches. So basically, we want to find out, well, how tall do men have to be? If women have to be 72 inches, we're assuming they're using a comparison to the average. So we're going to say, well, what would the z-score be for if you were 72 inches? So we're going to take the z-score for women and say, well, it needs to be, you have to be 72 inches tall to get in this club, but the average female is only 64 inches tall, and the standard deviation of women's heights is 2.5. So I'm finding the z-score that they're allowing, and the boundary. I'm standardizing this female height right here, 72 inches. So 72 minus 64 divided by 2.5 gives me gives me 3.2 standard deviations above the mean. Alright, so now I want to find the similar height requirement for men. So in other words, how tall does a man have to be? So if I look at my z-score formula, I'm looking for this value right here. I don't know it. How tall does a man have to be in this club? The average man is 69 inches. The standard deviation of male heights is 3 inches. And the z-score, we know, has to be 3.2 because that was the z-score for women. So now to solve this equation for x, I'm going to multiply both sides by 3. And 3 times 3.2 is 9.6. And then I'm going to add 69 to both sides. And so x would be, the men's height would have to be 78.6 inches at least. Alright, moving on. Suppose that I took a random sample of 9 students and recorded their score on a recent quiz. Their scores are listed below. Sketch a dot plot for this distribution and list all the summary statistics for this data. Mean, standard deviation, okay. So we can do this relatively quickly using our calculator, but we do want to make a dot plot for this distribution, so I'm just going to make a few more labels in here. Alright, so I'm just going to put a 30 here, you know, there's a 30 and a 35 and 36 and 40 and 40 and 43 and 45 and 45 and 50. So there's my nice little dot plot, and I want to find all of the summary statistics. So I'm going to go to my calculator, I'm going to hit Stat, Edit, I'm going to hit the up arrow and clear my list, and I'm going to enter 30, 35, 36, 40, 40, 43, 45, 45, and 50. And then I'm going to hit Stat Calc, one variable stats, list 1, calculate. And so I can easily list my X bar is 40.4 repeating. My standard deviation is 6.106. My N is 9. It means I have 9 observations. My min is 30. Q1, my 5-number summary is right here, is 35.5. My median is 40. And I'm just going to, if everyone's consistent and just uses the calculator, it saves everybody time. The calculator does calculate the quartiles a little bit differently than we might. So if we're all just consistent and use the values from our calculator. Alright, so now we've done all of this. Now suppose I was feeling generous. These are all test scores on a recent quiz. Suppose I was feeling generous and I wanted to add 5 to each point scored. Sketch the new distribution on the same scale. So now I'm going to go back to my Stat Edit. I'm going to edit my list. I'm going to go to list 2, and what I can do in the heading of list 2 is I can tell it by hitting 2nd and 1, and notice how it puts list 1 in there, and I'm going to add 5 to every value. So what I'm doing is I'm adding 5 to every value. So my new values that I need to plot are 35, 40, 41, 45, 45, 48, 50, and that's it. I must be missing something. And 50. Okay, so 2 50s. So now again, what I'm going to do this time is Stat Calc, and I'm going to do one variable stats, but this time all my data is in list 2, so I have to hit second list 2 and then hit calculate. So now I'm going to stop this video. The rest of it will be in another one. So